Hi class, Dr. Betts here. Welcome back to Chemistry 1032 Lab. Today we're going to discuss Unit 6, Organic Chemistry. Part 1, Modeling Organic Compounds. So you're going to be seeing some video with some models of organic compounds using a ball and stick model kit. We'll explain more about that later, but you're going to take these models, look at them, examine them, and kind of, draw them in your data sheet. Not a big deal, really. Kind of easy, but very, very powerful in helping you learn the structures of organic molecules and their classes. Part 2, you're going to be drawing these organic molecules, so you will just practice. You'll practice the different techniques of drawing organic molecules, and you'll learn the names of these drawings, skeletal formulas, expanded structural formulas, etc. Part 3, you'll be learning the classes of compounds, so you'll be practicing with the classes of compounds. Organic compounds, are broken into numerous families of compounds, and you'll just be practicing in those in an attempt to learn them. You do have to memorize them. And number 4, part 4, we'll be building our own organic kits, or organic compounds, using a ball and stick model kit if you happen to own one, or if you don't, we'll simply use candy. Yes, candy. Delicious, yummy candy. Part 1, Modeling Organic Compounds. Here we have an photograph of a basic ball and stick model kit. Now, this model is showing us a lot of different things. First of all, it's showing us 3 different colors: white, red, and black. There's also commonly used as blue. The colors represent atoms. Red is oxygen, white is hydrogen, and the black ones are carbon. It's kind of a convention. It's always that way with a kit. Every kit I've ever used, black has always been carbon, white has always been hydrogen, red has always been oxygen. There are blue, for example, is nitrogen. There are other colors, but these are the most common. And now what do I see here? I see a black carbon attached to another black carbon. So let's just draw that. So it's a carbon to carbon bond right there. This little gray stick tells me there's a single bond between the 2 carbons. On this carbon on the right, there's a hydrogen going down at about a 120-degree angle between there and there. Now, don't measure it with a protractor or anything like that. Just kind of give it a try. Give it an angle. Now, on that same carbon, right here, it appears to have 2 gray sticks going to it, doesn't it? One here and one here, going to a red ball. The red ball is oxygen. So the 2 sticks tells me there's a double bond there. So I draw 2 lines right here for the double bond, and I'll draw it in red. There's my oxygen right there. So this oxygen is that oxygen. These 2 gray sticks are the double bond right here. Now we have to deal with this carbon. Remember, really important that you remember that carbon always has to have 4 bonds. So right now, this carbon on the right has 1, 2, 3, 4. So its octet is satisfied. Don't draw any more on there. Let's go to this carbon right here. If you look over here, this carbon has a bond to another carbon, which we've already drawn, a bond to this hydrogen, a bond to this hydrogen, and a bond to that one. So this carbon has 3 hydrogens. 1, 2, 3, 4 bonds around carbon. That's how you do it. That's how you take a model and translate it into a drawing. This happens to be what we call an expanded structural formula. Okay? And that's how you do part 1. And you're going to identify the family of compounds, or the class of compounds as well. This happens to be an aldehyde. All right? All right, guys, that's part 1. In part 2 of today's experiment, you're going to be looking at different ways of drawing organic molecules. Now, in this particular example, I've drawn up the molecule, this is ethane. This is the expanded structural formula of ethane. Notice it has all the bonds, all the atoms are drawn in. So in an expanded formula, you have to draw all the atoms in and all the bonds. It gives the most structural detail. However, I think if you look at this drawing long enough, you're going to get a little bit weird. Your eyes are kind of going to get a little bit buggy. Your head's going to start to rebel against it. It's just sensory overload. There's just too much being given in one drawing. And this is only a 4-carbon molecule. A lot of organic molecules have, 10, 15, 20, 100, 300, 1,000 atoms inside of that molecule. You can only imagine how busy it would get if we didn't have a different way of drawing the organic parts. There's actually three different ways of drawing structure and one of drawing a formula. Okay, so now the condensed structural formula will abbreviate this structure and make it a little bit more, or maybe a lot more in your opinion, easy on the eyes. All you do is you take a pen or pencil, or you do this in your mind's eye, you don't have to do it on paper, and you just kind of draw little dotted lines down through the carbon to carbon bonds. And you say, okay, on this side of the line, what do I have? I have 1 carbon and 3 hydrogens. Well, that's a CH3. What do I have between these two lines? Just right here. I'll have a C and 2 H's. So that's CH2. What about here? Well, that's another CH2. You get the idea? And finally, right here, 1 carbon and 3 hydrogens, CH3. Okay? So that's how you convert an expanded structure to a condensed structure. Expanded structural formula to a condensed structural formula. Very simple, very nice. Okay? All right, what's next? Oh, a skeletal formula. A very, very common way of expressing an organic molecule. It's also one of the more confusing ones. Students sometimes have a little bit of a hard time with this. It's really not hard, guys. Let me take us up to here on the slide so I can have a little bit of working space. Let me just redraw our parent molecule. I'm just going to draw it in a slightly different way. That's all. Slightly different. And there's a reason why I drew it in the zigzag pattern. So now, when you're drawing a skeletal formula, first of all, you have to understand that the carbons and the hydrogens bonded to those carbons are never shown. Hydrogens bonded to those carbons are never shown. So the carbons are not shown, the hydrogens are not shown. They're never shown. Now, if a hydrogen is bonded to any other atom, say oxygen or nitrogen, you have to draw it in. But if it's bonded to a carbon or a hydrogen, you don't show it. Okay? All right, so let's do, the easy way to do this is just to show you the answer. Now, do you see how this one kind of zigs and zags? I'll do the same thing here. Up, down, up, up, down, up. How this works is that wherever a line terminates, that must be a carbon. Wherever 2 or more lines, could be more than 2, come together, that's also a carbon. So here we have a carbon. Here we have a carbon, because that's where lines terminate or stop. Here we have a carbon, and here we have a carbon. So wherever lines terminate, or where 2 or more lines come together to a point, to an intersection, that's a carbon. So in this particular molecule, there's a carbon here at the end, because that's where lines terminate. There's also a carbon here and here, because that's where 2 or more lines are coming together or intersecting, if you will. Remember, carbons have to have 4 bonds. They must have 4 bonds. If there's nothing else drawn on the carbon, it must be hydrogen. If there's anything else drawn, say chlorine or oxygen or nitrogen, something like that, then that's one of your bonds. Those must be drawn, however. You never assume oxygen or any other atom except for hydrogen. So this carbon, as it's drawn, has 1 bond right here. It has to have 4. It already has 1, so the next atoms must be hydrogen. So it must have 3. Same thing over here. This carbon has 1 bond, has to have 3 more, So they must be to hydrogen because nothing else is drawn. Same thing here and here. 1 bond, 2 bonds. So it has to have 2 bonds to hydrogen because nothing else is shown. Same thing here. 1 bond, 2 bonds. Must be 2 hydrogens. Every carbon must have 4 bonds. And there you go. So that's the skeletal formula that I converted back to expand it just to show you how it was done. Let me draw the answer down here though. There you go. There's the skeletal formula. Now the molecular formula is simply the total number of carbons, total number of hydrogens, and total number of any other atoms. In organic formulas, the carbon goes first, hydrogen always goes second, and then any other atom after that in alphabetical order. But first is always carbon, next is always hydrogen, and in this particular molecule there's 1, 2, 3, 4 carbons. And there's a whole bunch of hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C4H10. And those are the 4 different formulas in organic chemistry. 3 of them are structural. 1 of them is just a molecular formula. Commonly used, very, very commonly used. All three of them are very commonly used. Skeletal formula seems to be more favorite because I think you'll agree after you get used to seeing it, it's much simpler to use. Okay? All right, guys, that's the end of part 2. In part 3 of today's experiment, you'll be working with classes of compounds. Now, the only way to remember these is to memorize them. You know, I tell my students, make flashcards if you like, write them down, draw them, do whatever you have to do, but you have to memorize them. And part 3 is a little less, more or less an assignment. It's in your data sheet. It just wants you to look at these compounds, compare them to the other compounds you'll find in your manual, and try to identify which families is which. Oftentimes it helps to break them into divisions of the family, you know, oxygen containing, nitrogen containing, hydrocarbon only, those kind of things. Maybe break them up like that. That's what you have to do. You have to just take the classes of compounds that are in your book, memorize them, and be able to identify them by looking at them. So if I showed you a compound on an exam, you could go, oh, okay, Dr. Betts, that's an aldehyde, no problem. Oh, hey, that's a ketone, or hey, that's an ether or an alcohol, something like that. By the end of this experiment, you should be very, very familiar with all the classes of compounds. Okay? All right, guys. Moving on to part 4. In part 4 of today's experiment, you'll be building your own molecular models, either using a molecular model kit if you happen to have one, or if you don't want to spend the money on one, they are rather pricey. You can use candy. Yes, sir, candy. Nice thing about the way I want to do it with candy is at the end of the class, you can eat candy. So keep that in mind. Candy, I bought my candy at the local pharmacy, it cost me $1 a bag, and I bought some toothpicks. So you're going to need some candy and some toothpicks. Buy the multicolored candy if you can find a bag of numerous different colors. Preferably black and white would be really nice if you had some black candies and some white ones, but it doesn't matter, whatever colors are fine, as long as you assign the colors an atom. So if you have like, you know, red, green, yellow, and brown, just make sure you assign what color is what when you're reporting your model kits. You do have to take photographs of them and send them in for us to see. So now let me show you how to make models using your candy. It's very simple and it's very fun. Here I have a little candy. It's kind of purplish, so I'm going to call that black, and that's carbon. I was happen to get some nice white candies. You know, they came in the same bag, so I didn't pay any more money. So here's some. I guess they're white. In the camera, they look very white. They're kind of a yellowish color. And I had some red candies. So, I'll just never forget the bonds. The bonds are the toothpicks. And if you want, you don't have to do these with candies. You can do them with fruit. You can have some strawberries and grapes or whatever. A lot of chemists just play with fruit, and sometimes you see them playing with candy. We're just kind of weird people, us organic chemists. All right, so we're going to make a small molecule. We're going to make methane, CH4. All right, just CH4. Not a big deal. Here's my carbon, my C. I'm going to put the toothpick, literally, I'm just going to put it, so I get my hands out of the way there. Just going to put it in there. There you go. Nothing to it. That's a carbon, and that's a bond. I'm going to go over here and grab my white candy, and I'm going to put it in it. Careful not to stab yourself with these toothpicks. If you don't have toothpicks, you can take paper clips and bend them out straight. No problem. You don't have to spend a lot of money to learn chemistry. All right, so there we go. So there's a hydrogen here. There's my carbon there. Now, the next step is probably the hardest. A lot of students, they want to make their bonds right angles. But organic molecules are not right angles. They don't have bonds that are right angled to each other. They have bonds that are 109.5. Don't get a protractor. Don't go looking for your kid's math set or anything like that. Just kind of estimate it. This is 90, so 120. So I get this in a better view here. So 120 is right about there. And just stick it in there. I don't care if it's perfect. Don't care if it's perfect. I just don't want it to be here. Don't do this. Do not do that. That's not right. Let me see if I can get it better. Okay, it's not 90. It's 109, which is approximately there. So notice it's a nice, pretty big angle there, right? Now, all bonds have to be 109 from each other in a methane. Don't worry about measuring those angles. Just get them close. Just get them close. That's all I'm worried about. Get them close. On a model kit, there's pre-drilled holes that'll help you do this. And you pay money for those holes. I'm trying to save you some money, and I'm trying to get you to eat some more candy. All right, so now I'm going to put my next one in here. So I tried to get the bond angle 109 between here and here, and 109 between there and there. So there's my 3 bonds, right? Put a couple of hydrogens on this bad boy. It's not supposed to be hard. It's supposed to just be fun and kind of give you an idea of what organic molecules look like when they're done in 3 dimensions. It's not going to be perfect. It's okay. It doesn't have to be perfect. It's just to give you the idea of what organic molecules look like. So here I am holding the center carbon. 1, 2, 3. So right now I have CH3. I need 1 more carbon. And here we go. Here's my other bond. I'm going to make it as close to 109 as I can. There we go. And my hydrogen. Again, guys, don't worry about making these things perfect. Just make sure the angles are not 90 degrees. And there we go. There is a nice looking methane molecule. Let me get my notepad here so I can set it down for you so you can see it. There we go. Can't really see it very well, but can you? Hold it in my hand, I guess. There we go. Let me get it out of the way. There, that's got it. So there is a nice looking CH4. Notice it can stand on its own. If your model can't stand on its own like that, you've probably made the bonds 90 degrees, or you've made it flat or something's gone wrong. It should look kind of like this. Okay? And that's methane. That's, fairly simple, but, this is how they're made. So all carbons with 4 single bonds have this particular sort of shape. Okay? So we set that aside. Let's do one more. Let's do a simple aldehyde, formaldehyde, for example. Formaldehyde is CH2O. So I need a carbon. Only 2 hydrogens now. I'm going to tell you, it's really tempting to eat these candies right now. They kind of smell good. And here's my oxygen. So I have my oxygen, carbon, and 2 hydrogens. Now in formaldehyde, CH2O, carbon has a double bond to oxygen. Double bonds are simple. Grab 2 toothpicks or 2 paper clips or however you're doing it. Stick 2 paper clips into your black gummy candy. Just like that. So I have 2. Let me space them out a little bit so you can see them. There we go. Doesn't have to be perfect, guys. Doesn't have to be perfect. It's not going to be perfect. But just get the idea of what these things look like. There's my double bond. And now, put candies on top there. There you go. That is a carbonyl, a carbon to oxygen double bond. Oxygen's here, carbon's down here. Now, this bond here is going to be a hydrogen. It's going to be here somewhere. It has to be 120 from here. So this is 90. That's about 110. That's about 120. I didn't measure it. I guessed. I eyeballed it. Okay? I don't want to measure it. I don't have a protractor. Neither do you. Maybe you do. If you want to measure it, go ahead. You don't have to. Just get it close. Get the idea. Okay? And here we go. Something like that. Don't forget the hydrogens. Don't forget the hydrogens. Here we go. Here are my white hydrogens right here. And there she goes. And then over here. Here we go. There it is. Look at that. Formaldehyde. Formaldehyde. For the low cost of, I think it was $3 total for this. 2 bags of candy. I only needed one. Got 2. And some toothpicks. And you can reuse the toothpicks. You know, even though you stuck them in candy, they're not spoiled. They're not wet or anything. You can still use them. And you can eat the candy. But please wait to eat the candy till the end of this class. End of this course, excuse me, because we are going to use it again in this class. All right, guys. Now, I hope this was a little bit of a nice, fun introduction to building your own organic molecules. You're not going to make them perfect. You know, your angles are going to be off slightly. No one's measuring this. Just make it look sort of like this. All right, guys? All right. Now, good luck with this. Have fun. And don't eat your candy till the end of the course. All right. See you later. I want to wish you guys good luck and good chemistry. We'll see you soon.